This is an example of an AC mesh solutions problem in Circuit Tutor at level 2, or the medium level. As always, we do have examples available at various levels of difficulty, and it would be a good idea to view some of those to give you a better idea how to work the problems. So we're going to go straight into a level 2 problem. Now, because this is a solutions game, we are being given the KVL equations, so we don't have to worry about writing those for the, in this case, the meshes that are involved, or super meshes as it may apply. In this case, it's just meshes. We do, however, have to write a current constraint equation for each current source in the problem. Notice that there's one current source here. And I should also mention that the mesh currents have been automatically labeled for us, and by default the reference mesh has been chosen to be the outer mesh. So the counterclockwise traveling outer mesh current has been set equal to 0 by default. So that's not included here. And then the SOT variable equation, we have to write that for the voltage V0, which is the voltage across this 5 ohm resistor. So let's go ahead and do that. So the current constraint equation, if we observe this current source, we see that only one mesh current, since the outer mesh current is being set to 0 as a reference mesh, only one mesh current travels through that in the direction of the reference arrow of the source. And so therefore that will have a plus sign, and we just need a term with one mesh current. We don't try to subtract I0 or anything, because I0 is just not, notation is not used in Circuit Tutor since it's already 0. So we set that equal to a fixed value, and as I said, we won't need a minus sign. Now if the current source arrow were going the other direction, then we would need a minus sign out in front of the complex number. And remember that the magnitude itself of the complex number can never be entered as a negative number, because magnitudes by definition are negative, but you can precede the entire complex number by a minus sign. That just really means that you're changing the phase angle of the complex number. And you can also do it by changing the phase angle, for example. So this is going to be I1, and I1s is 3 angle negative 60 degrees. So enter that. And just as a matter of interest, I'll point out that I could have put a minus sign here and added 180 degrees if I like to make that 100 and plus 120, but there's no real reason to do that here, but it will be accepted as a correct answer in Circuit Tutor. Okay. Now we've written the one constraint equation that we need. Now the SOT variable equation will be this voltage V0 across the 5 ohm resistor. So we choose, that's across a single element, so it would be called a SOT branch voltage. And of course the variable is V0. And so that's equal to, and now we see that there is a single mesh current here going through that resistor, since the outer mesh current is being defined as 0 in this problem. So we would use this type of term, and you see from the tooltip there that that's what that is. And so we'd enter mesh current, I'm sorry, that should have been I2, times, in this case, just 5 ohms. Now if that were a complex impedance, we'd enter that here in rectangular form. Impedances are always entered in rectangular form in Circuit Tutor, but in this case it's just a resistance, so that's straightforward. Now we do need to check, however, as always when we're using Ohm's law, we need to check the sign convention. So for example here, this current is going up through the 5 ohms since it travels clockwise, and that's going into the positive side of V0. So indeed I will need a plus sign here, but remember that if V0 had been reversed in terms of its reference direction, then we would need a minus sign. So about half the time you will need a minus sign in your Ohm's law expressions, or the V equals IZ expressions, and it's very important to always check that, otherwise you'll get a lot of errors. Okay, that is correct, and now we've written all of the required equations, so we'll just click no more equations. And now what's new in the solution tutorials is we do need to go about solving these equations. And eventually we'll use this SOT variable equation. For right now, we want to put these into standard form, meaning that we combine the coefficients of each variable, like say I2, for example, or I3 or I1, and then we put all the constants, if any, on the right-hand side. So like there's a constant, for example. In doing this, we are allowed to multiply through by a constant, although we probably wouldn't need to do that in mesh analysis typically. You cannot, however, make substitutions of one equation into another. So we couldn't, for example, take this value and use that to replace I1 down here, for example. That would not be accepted. We're going to do that when we solve them, but not when we first write the equations in standard form. Okay, and remember, we don't put the sought variable equation into this form. That's just the first three equations only. Okay, so the first equation is very simple. It just says I1 equals that constant. So I1 will, of course, have a coefficient of 1. The others would have coefficients of 0. And then we just put the 3 angle negative 60 degrees there. Now the second equation, which would be a KVL equation, the I1 coefficient will be 0 since there's no I1 terms. For I2, we have a coefficient of 5 and then a negative J2. So we just add those numbers together mentally, and that would just be 5 minus J2. And then the I3 will have a coefficient of just negative J2. And notice that there is no constant term, so the right-hand side will be 0. Then the next equation, we first look at I1, and that has a coefficient here with the two minus signs being multiplied of just J6, right? The minus signs would cancel out there. So we'll just enter that as J6. And then I2, the only term here is this one, and that would have a coefficient of the minus J2, using both the minus sign and the number. And there's no other I2 term. Then I3, we would have a coefficient of J2, and then also a coefficient of negative J6. So adding those up in our head, that would just be negative J4 for the I3 coefficient. And that one doesn't happen to have any real part in this problem. And then the constant term would be this term added to both sides of the equation to bring it over to the right side. And of course, that would just give us 3 angle 0 on the right side. And remember that these magnitudes of complex numbers must always be positive. It'll give you an error if you try to put a minus sign there. And if you did need a minus sign for some reason, such as if, say, that would have been a plus 3 angle 0, then you would basically do that by putting in a 180 degree phase shift over here. For example, you could enter 180 or negative 180. Either one would work for this angle. But it should always be, the angle should also be in the range from negative 180 to plus 180, which is the standard range typically we use for complex number angles. Okay, so we're done with that. We'll check the equations. Oh, looks like we have a mistake here, so let's take a look at that. So that's the second one. So there's no I1 term, and we had 5. Oh, I don't know why I put a minus sign there. That should have just been, I must have been looking at the other minus sign. So that should have been 5 plus J2, just a silly mistake. And notice that all the incorrect, all of the incorrect equation is turned yellow. It doesn't mean that every term is wrong. It just means that you have a mistake somewhere, because it can't analyze basically which term is correct, since you could have multiplied this by a constant, for example. And then we'll just double check the I3. That's the negative J2, so that should be correct now. And of course, it does allow you several attempts here in case you make a silly error like that, but obviously try not to make any errors. Okay, so those correct equations now have been printed on the screen, and now the next job will be simply to cast those as a matrix equation. Now, I'm not really recommending that you solve this as a matrix equation. I mean, you could do that potentially using MATLAB or maybe some online app, or there's even some calculator programs that will do that with complex numbers. But really, that's probably not the best way to solve this problem. We're simply going to use elementary algebra, and I'll show you how in a moment. But let's first put these in a matrix equation, and that's very easy. Here we just push the button to copy the coefficients, and so we don't have to retype all of them, but you could if you wanted. And remember what this means. For example, we have this times this, plus this times this, plus this times this would be equal to this. That's the first equation, if you just remember how matrix multiplication works. And for example, this one times this, plus this times this, plus this times this equals this. And that would be the third equation, and similarly for the second one, the middle row. Okay, so we check that. And now the next job is to solve the equations. And again, what I typically recommend is start just with the KVL equations. Those are always the most complicated ones. And we're simply going to substitute the constraint equation into that. In this case, it's very simple. It's just a constant value. And that will make this into basically a 2x2 system by eliminating one unknown immediately. I mean, we could have, in theory, written the equations that way, but Circuit Tutor doesn't really allow you to skip that step. So we'll just do it here. And a 2x2, of course, that's very elementary. We don't really need matrix methods for that. We'll just do it on paper as elementary algebra. And remember that when you're doing algebra with complex numbers, it's exactly the same as doing it with real numbers. All the techniques that you use with real number algebra would work here as well. It's just you have to do complex arithmetic, which of course is a little bit more complicated, and it would require typically a calculator to do that. Okay, and your instructor might ask you for a copy of your handwritten algebra that you do. So if they do, then you would keep that for them and turn that in. Otherwise, you might want to keep a record of that just for yourself so you can review that later when you're studying, just to remind yourself how to do the complex algebra. Okay, so we need to enter the values of the three mesh currents. Now, notice that we really only need I2 here. So if you wanted to kind of skip calculating all three, you could just skip this and enter the final value of V0. But I'm going to go back and check all three just as a useful check to make sure we didn't make any mistakes. So now I'm going to do the algebra on paper, and that's illustrated here. So what I've done is, again, just copied the simplified form of the two KVL equations, which are the second and the third row here. So I wrote 5 plus j2 I2 minus j2 times I3 is equal to 0. And I used bars to indicate the complex numbers. And the second equation just was j6 I1 minus j2 I2 minus j4 I3 is equal to 3. So that's just this. And remember, I don't really need the angle 3 in rectangular form. That's just a 3. So I just wrote it this way for brevity. Now, again, I also know from the constraint here that I1 is just 3 angle minus 60 degrees. So I'm going to plug that in right away. It's not present in the first equation, but it is here. So I will simply rewrite this equation down here, copying these terms down. I just omitted some parentheses. And then subtract this off now. Since it becomes a constant when I make the substitution, I subtracted it from both sides to group it with the other constant over here. So now I have 3 minus j6 times the I1. So the I1 I've just substituted in here. And now we can just evaluate that expression on a calculator. And I guess I can illustrate that for you using a calculator emulator here. This is a TI-84 plus type model, which would be similar to any TI-83 or 84 really. The TI-89 is actually a little easier to use, but it's also similar, just it has a better behavior of the degree and radian mode. Okay, so we'll just enter 3 minus, and I'll just write that as I6, and actually I'll just write that as I18, since that's easier. Enter it that way. And using implicit multiplication there, and then we need to give that an angle, minus 60 degrees. And first of all, I should have mentioned we always want to check that we're in complex mode for the calculator. If you try to do calculations in real number mode with complex numbers, it will not work or give you the correct answer. So I had already, I'd kind of like this in polar form. It doesn't really matter. I could select either one. But I always want to go into the mode here and make sure that down on this row here that I have selected either polar or rectangular, as you prefer. And generally you want to be in degree mode here if you're getting a polar answer, because that's what's generally required in Circuit Tutor. So I've already done that, and I'll just exit that. Okay, so we had the three, I have to go back over now. Okay, and so now I'm going to do a trick here, because this calculator doesn't allow you to enter angles directly in degrees. So I'm going to use this predefined variable e that I always use to simplify this type of calculation, and that again was just little e, the base of the Neperian logarithms raised to the power I pi divided by 180. And when we raise that to the power of this angle, which is in this case the negative 60, that will in effect convert the degrees to radians as is required in this calculator. It will not accept an argument of a complex exponential in degrees, which is a peculiarity of this calculator. On the TI-89, for example, you wouldn't have that issue. Okay, so we've entered our expression here, and I'll just push enter. And that will give us our result in polar form of 15.47, angle negative 144.4 degrees. Remember, that's, of course, the argument of the cosine. And I'm in degree mode. Always make sure you know what mode you're in, because if that's in radians, then that wouldn't be obviously degrees, and you'd have to be careful in using that later. Okay, so now I'm going to take my first equation and just rewrite it down here for convenience. And I want to basically, there's various ways to do this. I could solve this first equation for I2 by adding J4 I3 to both sides, and then dividing by the coefficient negative J2. That would give me I2 in terms of I3, and then I could plug it into here, for example, and that would give me a single equation involving all I3 terms, which would allow me to solve. Or I could solve for I3 here by a similar process, adding this term to both sides and dividing by negative J4. And then substitute the I3 into here, or I could solve this equation for either variable and plug it in up here. Whichever you prefer is fine. In my case, I'm going to multiply this second equation, and I'm going to remember actually that in the problem, the variable I really need is I2, so I'm going to choose to eliminate a different variable there. So I'm going to try to eliminate the I3, so I get I2 directly. And so to do that, I'm going to multiply by this coefficient divided by this one. So I'm multiplying the entire equation through by negative J4 divided by negative J2. And we can see mentally, obviously, the negative J's cancel, and that 4 by 2 is just 2. So I'm really just multiplying this equation all by 2 angles 0, if you like, in polar form. And by doing that, then if I subtract this equation that's been multiplied from this one, clearly, the negative J2's will cancel out. I'll just have negative J4 here, which means that the I3 terms will cancel, just giving me an equation involving only I2, which is, of course, the goal. So doing that, then we have first the negative J2 I2, and I factored out the I2 here. And then we can, of course, the I2 goes away, so we just have basically, I'm sorry, the I3 goes away, I meant. So we subtract the this multiplied by 2, which is then 10, and then we subtract also the what's now J4, and we multiply by 2. So I distributed the minus sign into both of those there. And then the right-hand side, again, I didn't multiplying the 0, of course, doesn't matter. So that subtracted from this is just the original value, which I copy here. And then I just simplify that before entering in the calculator as negative 10 minus J6, adding those two complex parts together, or the imaginary parts together. And then I simply divide this result here. And I can just do that here, just using the answer automatically divided by that quantity. And of course, I have to put this in parentheses. So I would go negative 10 minus, and then the J would be I6, close parentheses. And again, if you don't use parentheses, of course, then it would only be dividing by the first number by order of operations, and that wouldn't be the correct result at all. So just press enter there, and that will give me the value of I2 bar, which is 1.327 to 4 significant digits, again, for accuracy. Angle 4.60 degrees is probably enough, since that's a very small angle. And then I take that result, and now I need to solve for I3. Now, I really don't need the I3 bar, and again, if I want to skip that part where I enter all the mesh currents, I could, and just use this to find the sought voltage. But just for the completeness, I'll substitute back. And so I'm going to use, for example, this second equation is the easier one, because it's simpler. And so I'll solve this for I3 bar just by basically, and again, I don't need the multiplier here, so I'm just using the equation inside the brackets. So I will just subtract this term from both sides. So I have negative quantity 5 plus J2 times the I3, which is this value, so I've inserted that there, divided by the coefficient here of I3, which is negative J2. And then those minus signs cancel out, as I've crossed them out there. And again, we can just enter that on the calculator. And in this case, I guess I could just do that quickly. That would be times that quantity 5 plus J2. Again, close parentheses. Again, once again, we must use parentheses. Divided by, and here's another point where we can't just write J2 here, because if I did that, I would be dividing by the I and then multiplying by the 2. Remember the way order operations works, you have to use parentheses on a product like that. So this would have to be parenthesis I2 close parenthesis. Otherwise, again, if you omit those parentheses, you're going to get the wrong answer. So be very careful about that. Okay, and that would give us the answer there, which is 3.573 angle negative 63.6 degrees. Okay, so I'm with the calculator, and we'll just enter those numbers now into the form in Circuit Tutor. So we have 3 angle negative 60. That was the one that was given to us essentially. And then the I2 is that 1.327 angle 4.6. And then the I3, that's that 3.573 angle negative 63.6. Okay, so we'll check that. And those are correct. And then the last step is to use this sought variable equation, which is pretty simple. So we just have to multiply I2 times 5 to get the sought quantity in volts. So that's a very simple calculation. Remember, when you multiply I2 times 5, the phase angle here is not going to change. We just have to multiply the magnitude because 5 has an implicit angle of 0. And so just doing that simple math in the calculator for the magnitude, if you will, we would get 6.635 angle that 599 if you like. And we'll check that. And that is correct. And then the last step is to do the inverse phasor transform, to take the V0 phasor and put that into the time domain, which is what we normally want in an AC problem, because the real world, of course, is in the time domain. So to do that, we'll do that in this form. And the first thing we need is the omega. Remember that whatever multiplies t in the argument of a cosine, that's by definition omega. It's not f. If you happen to be given f here, you'd have to convert that to omega. Remember, omega is 2 pi f. But here we're already just given omega, and it's 10 kiloradians per second. This text box will not accept a metric prefix. It'll give you an error if you do that. So we'll just enter that as 10,000 instead. And then the phase angle here for the V0 was that 4.6. Would be good enough. And then the magnitude is the 6.635. And of course, here it's telling you that it's cosine, but if you're doing this on paper, you will always need to remember that phasors are based on cosine functions, not on sine functions. So that's important to remember that. Okay, so that is correct. And that does complete the problem. If you wanted to have a more detailed explanation, for example, of how these KVL equations that were given to you are derived, we can get that, or details about the sought variable equation. So you just answer yes there if you do want to see that. And again, you can also get really detailed explanations of the KVL equations if you click this as you cycle through them, or the constraint equations are also explained in general here. So that will conclude this problem.